maybe I have different format. So let's start. My name is Yury Karavaev. I'm from Ижевsk State Technical University and represent the Department of Mechatronic Systems. My topic is brushless DC motor control algorithm for national Sphero robots, actuators. As we seen from reports our colleagues about control and dynamics model of Chaplin's ball with rotors, we name this ball Sphero robots. The robots that consist from rotors. There are different problems to control this object. For realization complex, for realization the movement of this ball on any trajectory, we need brake and accelerate the rotors anytime. And set needs special requirements to the motors. By analysis of construction and control algorithm of these Sphero robots, we formulated the requirements to such motors. The first one is that this motor should be able to generate enough torque. The second one is the motor must have electrical efficiency more than 70% over the full range of the rotation speed. The third one is the minimum mass of motor by given power. And the last is the rotation speed. We need the rotation speed in range from 0 to 7,000 revolutions per minute. The analysis of all electrical machines, all motors, has shown that only BLDC motors can satisfy these requirements.
What is BLDC?
BLDC, brushless direct current motors. Here you can see the advantages of BLDC motors. They have good torque, high reliability, high efficiency, and high power to volume ratio. But there are also problems, and the main is that we need to increase the electrical efficiency at low and ultra-low frequencies of rotation. The existing drivers and controllers of such motors are used mainly control modes of rotation in range from 20 to 100% of the nominal value. And by our task is to develop the system in all range of these speeds from 0 to 7,000 revolutions per minute. Here you can see the typical motor driver, BLDC motor driver. This is transistors module. This is three-phase BLDC motor here. This is the photo of the typical BLDC interface circuit that allows isolation and amplification of signals from microprocessor. And
the size, how big is this?
This motor, for our application, the diameter of this motor is circa 4 centimeters. 4 centimeters, and length 6. Here you can see the ideal signal which we need to drive this motor. And the task of our control system is to generate the control signal near to this ideal sinusoid, sine wave. There are different algorithms to build these signals. There are 4. The first one, unipolar pulses. You can see that the sine wave generates as a meander. The second is the unipolar pulse width modulation. This pulse signal we generate as the more signals. Then bipolar pulses. Here we are used the bipolar signal of sinusoid. But here we change the duty cycle of signal, and that can be get the sinusoid. And the better and the best of this mode is the bipolar pulse width modulation. We change here the pulse, the duty cycle of pulses proportional to the sine wave function. To control the speed of the motor, we change the duty cycle of the impulses and frequencies of the impulses. So now I will compare all these methods. According to the theory of Parseval, we compare the energy in time domain and energy in frequency domain. And according to the theory of Parseval, they are equal. The frequency domain we get through the discrete Fourier transformation, and that can help us to calculate the electrical efficiency of every modes. The electrical efficiency is calculated as a ratio of energy considered to the first harmonic of current supply to the total energy. Because we need to drive and to control the motor in low and ultra low frequencies, we choose the sine wave 1 Hz, only 1 Hz. It's very low for this application. The spectrum of this signal, you can see it in this picture. It's only 1 Hz. It is ideal signal, and we will get this signal different modes. The efficiency of this electrical efficiency of the signal is on. So the first one, unipolar pulses. Here is the time domain, here is the frequency domain. You have seen here clear the third and fifth harmonics of voltage. These harmonics have very negative influence on the motor, because on these frequencies motor get low oscillation of rotor and heat evaluation in winding of motors. Here we get the current frequencies. By this mode, the current corresponding to the third and fifth harmonics are very has a big value, and that is very negative. And the efficiency, electrical efficiency for this mode is 0.8817. The unipolar mode, we have generate PWM. PWM is pulse wide modulation. Pulse wide modulation signal with frequency 50 Hz. The frequency domain is shown on this picture. You can see this 50 Hz. Here also we have third and fifth harmonics of signal. It's also not so good. This is the current spectrum of this method, and electrical efficiency of this method is...
Electrical efficiency is what divided by what?
That is here. This is That is current on first energy corresponding to current on first harmonic to all energy on all harmonic. When we generate PWM pulses on frequency 80 Hz, we get this figure. And we can see that we have this 80 Hz harmonics. But here also the third and fifth harmonics are very big. By increasing of PWM impulses, these peaks moved to the right. Here is the electrical efficiency of this signal. Then we can simulate the unipolar PWM with duty cycle. We change duty cycle according to sine wave. You can see that here. The duty cycle of impulses is changing. This is the frequency domain of these impulses. Current. The first harmonic is here more than in previous example, but we here have also negative influence of high harmonics. But energy efficiency is larger. And now, for example, if we, it's also this signal, but PWM is not 50 Hz, but 20 kilohertz. It really complicated to see this in this picture, but here we see that we have only one harmonic, and it's very big. In this case, in this example, we have energy efficiency 0.9957. And the next, we have simulated the bipolar PWM at the frequency 50 Hz. We have also the character is also near to the previous examples. The current spectrum of this signal. And now we change the duty cycle of this PWM signal on the frequency 50 Hz. Here you can see the sine wave. This is just for example. And for bipolar impulses, we change the duty cycle. Here is the frequency domain of this signal. This is the current spectrum of this signal, and energy efficiency is more higher. And now I can show you that we increase the PWM impulses to 1 kilohertz. Each impulse, each pulse from this page, from this figure, we generate as 1 kilohertz pulses. Each pulse. And we get this figure. You can see here that we have only one harmonic, and the energy efficiency here is 1. By increasing the PWM frequencies, we get better result, but it's limited by induction of coil of windings of motor. To lower the low induction of windings allows high frequencies of PWM. And we can choose from this simulation and modeling the right way to control the PLDC motor for such application as Sphero robots, except on low frequencies and ultra low frequencies, not frequencies, but speed rotation of products. That's all. Thank you for your attention.
Questions?
I'm interested in the geometrical sizes of your motor, why they are exactly of this size. Is it corresponding to the robot that you want to
Yes, exactly. We have previous calculation of model of robot that is 40 centimeter in diameter, and for especially mass we have choose that's 40.
I'm curious to know how small can you make them in your lab? for other applications.
How small?
If you can make smaller in your lab, do you think with your how small can you make it like 10 times smaller?
Yes,
than this size?
we can make that very small. With this method of bipolar with bipolar PVM modulation, we can do it very small.
And, what would be?
But the value of I can't answer exactly because it's different. It depends of special motor for resistance, for induction of windings of motor.
And this one, but it's this one. How much does it weigh? Because it's like it's 4 or 5 centimeters. Is it heavy?
A robot or
No,
motor?
the motor.
Motor is, I think, less than 100 grams.
What would be? I saw now. I forgot in the beginning which the biggest frequency that it can go.
Biggest frequency,
You're
7,000 rotation speed.
Yes.
7,000 revolution per minute
So
or more. But for our need, we need not more than 7,000.
So go from 7,000 to almost zero.
Yes.
Same motor.
Yes.
Okay.
Okay, let's have the speaker again.